Welcome everyone, this is week 1 day 3 outro. Let's talk more about model fitting. My name is Kening Wei. I'm a professor at the School of Psychological and Cognitive Sciences, Peking University, Beijing, China. My lab is working on human model control and learning. I'm interested in human model behavior in general. The tools I'm using including psychophysics, virtual reality, modeling, and brain stimulation. If you are interested in my research, please hit the link below. That's my lab website. Okay, what did we learn today? Today we learned how to use maximum likelihood estimation to do model fitting. Sometimes this is equivalent to minimize the mean squared error. And use a linear regression as a starting point because it is one of the simplest model we can get. And once we get the model parameter, we can estimate its uncertainty by using bootstrapping. And then if we want to evaluate model performance, sometimes doing model selections or model comparisons, we have to deal with bias and variance trade-off. To do that, we use cross-validation. In the outro, I will first do a quick review of what we learned today. Then I will give you a complete example to show you step by step how we use model fitting in real scientific questions. Lastly, I will extend what we learned today from those simple linear models to generalized linear models. All right, first thing first, let's do a quick review of what we learned. First, I would say maximum likelihood estimation is from a frequentist perspective. From a frequentist perspective, we think of data coming from generative models. That is, there is some underlying model or process that can give rise to the data. So the current data we have is model plus noise. And by maximizing the likelihood, that is the probability of the data given a parameter, we can estimate the best parameter. So this gives us some point estimate of parameters. Then we can use Bootstrap to get its confidence intervals. Then how are we going to interpret the parameter and its confidence interval? From the perspective of frequentist framework, the estimated parameter is most consistent with the current dataset. Why is this? Because from the generative model, we can generate a lot of dataset, right? Currently, we only have one single dataset. And the parameter we have is our best guess of the parameter. And then we cannot say that 95% confidence interval covers the true parameter with a probability of 95%. We cannot say this. Instead, we can only say if we generate samples for a large number of times, confidence interval is the theoretical range that it will cover the true parameter for 95% of the times. So this 95% carries the meaning of frequency of occurrence. The competing Bayesian framework will view it very differently. The Bayesian framework basically estimates the posterior distribution, that is, the distribution, the probability of parameter given the data. This posterior distribution can be estimated by combining likelihood and prior. Likelihood is what you learned today, that is the probability of data given a parameter. And the prior is our prior knowledge about the parameter. So I would say, in the Bayesian framework, first you have some prior belief of what the parameters are like. Then you use the new data, that's the likelihood, to update this belief. So you combine these two and get the posterior distribution of the parameter. So the confidence interval becomes very simple. It is just the probability of this posterior distribution. So compared to the Bayesian framework, the frequentist framework has its own limitations. Basically, when you're using maximum likelihood estimation, you completely rely on a current dataset. So that makes you subject to biases of a particular random sample. Also, because you did not consider the prior knowledge of the parameters, sometimes your search of the best parameter becomes computationally expensive. It's like when you search the best estimate, if you don't use prior knowledge, your search space is larger. So sometimes it is computationally more expensive. Nevertheless, once we use maximum likelihood estimation, we still want to evaluate our model performance. This leads us to bias and variance trade-off. And basically, it says if we increase the model complexity, the bias will decrease, but the variance will increase. So when your model becoming more and more complex, you can fit the data better. Your bias decreases, but the variance, because the model becomes more complex, it captures the variance from some unwanted noise. That's why the variance will increase. On the other hand, if we decrease the model complexity, the bias will increase, but the variance will decrease. So this is so-called bias and the variance trade-off. How can we deal with this? We use cross-validation. For example, if we have a 10-fold cross-validation, you basically divided the original data set into 10 pieces. You use 9 pieces as a training set to train your model, to estimate your model parameters. Then you use the last piece as a test set. The test set will give you a test error. Test error is a very good indicator of model performance because it does not monotonically decrease as a function of model complexity. Oftentimes, it can give you the best model complexity because it has corresponding to the minimum test error. So that's cross-validation. And the bootstrapping is another story. Bootstrapping is also resampling our original dataset. Using this as an example, say you have a linear relationship between visual contrast and the number of spikes of in the neuron you recorded. And this is your original dataset. Of course, you can perform a simple linear regression. You get is a parameter, that's theta 1, that's the slope. And when we do Bootstrap, we just resample the original dataset to create a new dataset, that's right here. Then you will find, because of the resampling, some older data will have repetitions in the new dataset. This is a case 8 in the original dataset. You see it repeated twice. And the case 6, it repeated twice too. So you do this, once you get the new dataset, you can compute the model parameter again. And you do this many times. You get a lot of model parameters. And in fact, you can derive its distributions. Once you derive the distribution of theta 1, you can estimate its confidence interval on this distribution. So this is bootstrapping. So if we compare cross-validation and the bootstrapping side by side, we immediately realize that both are resampling method. And they just resample the original data set, iteration by iteration. So that's why they're both computationally expensive. But there are 7 different purposes. Cross-validation is very good for estimating model prediction error. That is, it gives you a performance measure of your model. So you can compare between models, you can do model selections. But bootstrapping is trying to estimate the confidence interval of your model parameters. This is very different. And because they have different purposes, so they're using different approaches. Cross-validation split the data into multiple sets, and there is no overlapping between these data sets. This is a requirement for cross-validation. But bootstrapping is different because you basically clone the data, or I can say you extrapolate the data to create more sets. In this sense, you have overlapping data sets. And because they're using different techniques, they have a different requirement on the sample size. For cross-validation, we need a large sample size. In fact, the larger, the better. For bootstrapping, we are perfectly fine with small samples. This is the biggest advantage of bootstrapping. We are just good at dealing with the small samples for estimating the confidence interval. So that's basically what we covered today in terms of maximum likelihood estimation. Next, I will give you a complete example and to show how we're using this kind of knowledge in doing real scientific research. All right, the second part of my outro I will give you a complete research example to demonstrate the two major uses of model. The first use is model parameter estimation. The second is model simulations. We generally follow some steps to build and fit a model. The first step, you need to conceptualize a model based on your theory, on your prior knowledge, or your hypothesis. Then you need to write down equations. You need to mathematically formulate your model. The third step, you need to do model fitting. This is what you learned today, so we can estimate those model parameters. The fourth step, we can do model simulations. We make new predictions and trying to compare those predictions with empirical data, see how good the model is. The fifth step, you need to interpret the model parameters. What do those model parameters mean? The last step, ideally, you can make new predictions from the model beyond what you have, beyond your own data. So my example study is from one of my papers published in 2008 together with Conrad Curtin. It's called the relevance of error, what drives model adaptation. It's a simple human behavior study, but it does has a mathematical model. So my research question is very simple. Should I adapt to visual error? I show you one example. If you shoot a basketball to the basket, sometimes you miss it, so you detect a visual error. If you know that you miss, the visual error is caused by your own mistake because you did not use the right amount of force, then in the very next shot, you should correct for your error. But if you understand that your miss is caused by some irrelevant factors, for example, a strong wind blow the ball away, then you should not adapt, right? That visual error doesn't count. So will people actually doing this kind of a causal inference in their brain during model adaptation? We will find out in the experiment. So imagine you're one of the subjects here, and you are moving your hand underneath a projection screen. So your hand motion is concealed by the projection screen. And you move your hand from one starting position to a target position, indicated by the red dot here. And the blue line is one movement trajectory. I won't show your hand during the movement, but at the end of the movement, I will give you a visual feedback indicated by the green dot to indicate your hand location. As you can see, the visual feedback actually did not match with your actual hand location. This is called a visual error or visual perturbation. I perturbed your visual feedback. And I can apply different size of a visual error from 0 to 8 centimeters. The error is symmetrical on both sides. Sometimes it's positive, sometimes it's negative. So what I expect to learn from these visual errors. Say, if I give you a positive error, next time you move downward to correct for this error. If I give you a negative error, next time you will move upward to correct for this negative error. So my prediction based on causal inference will be very simple. If the visual error is small, then it's more likely it's caused by yourself. Then you should adapt to it. If the error is too large, it's more likely it's caused by irrelevant factors, just like the wind blow the basketball away. Then you should neglect the visual error. All right, so this is our experiment setup, and we simply ask people to doing simple point-to-point wedge, and we will examine how they will adapt to the visual perturbation. Will they change the hand movement in the next trial? If they change the hand deviation, if they change the hand movement in the next trial, that's the indication that they learn something from the visual error. And then I further formulate my idea by using a graphic model. I think in the model system, you need to do causal inference between two scenarios. One scenario is the visual feedback, the visual error is relevant. In this sense, people can estimate their hand locations by using perception cues and the visual cues. because the visual error is relevant, he should combine these two cues together to estimate the hand location. If he knows the visual error is irrelevant, then he should disregard the visual error, simply use perception to estimate his hand location. So every single time, every single trial, he needs to estimate which scenario is more likely. And this gives out a very simple prediction of the data. So on the x-axis, I plot those visual errors I apply to the subject. On the y-axis, I show the hand deviation in the next trial. The hand deviation in the next trial indicate how much people learn, right? So I will predict people will show a learning curve like this. That is, for small errors, they will show a negative slope. A negative slope means if I give you a positive arrow, next time you will move in the opposite direction. But with increasing visual error size, people will no longer believe that the visual error is relevant, so they will reduce their learning. That means the learning curve will show this kind of a sigmoid shape. It will not further increase the hand deviations with increasing visual errors. So then I formulate my model in mathematical terms. The model takes a form like this. On the left-hand side is your hand location, is your estimated hand location. On the right-hand side is x-vis is the visual perturbation I apply to the subject. And x-hat hand is your estimated hand location. These two terms actually are observables. They are in the data. Why? Because in the very next trial, I can measure how much your hand deviates. That I will use as a proxy of your hand estimation. And the x-vis, this is the visual perturbation I applied. It only takes value like a 0, positive or negative 1 centimeter, or positive or negative 2 centimeter. This is the visual perturbation I applied, so this is also known. But there were 3 free parameters, that's S, sigma, and C. Those free parameters are not known beforehand. I will just give you a rough sense what do they mean. So S is a scaling factor. It basically tells you how much you will learn from a visual error. Is a percentage measure. Say if it's a 2 centimeter deviation, a 2 centimeter visual perturbation, if you learn 50%, you will correct for 1 centimeter. So S is a learning percentage. Sigma is a size threshold beyond which a visual perturbation is not corrected. So different people have a different threshold. If the visual error is too large, I will disregard it. But the different people have a different tolerance threshold. This is captured by sigma. And the C is a constant. So these 3 free parameters are not known beforehand. This has to be derived from our maximum likelihood estimation. This is exactly what we learned today. So as you can see, my model also assumes Gaussian noise. This is why you see a Gaussian sign here. And so we can just simply using maximum likelihood estimation to derive those free parameters. All right, let's take a look at the human data first. I plot some raw data right here. So on the x-axis, this is from one typical subject. On the x-axis, I plot the 9 kinds of visual errors I apply to the subject. On the y-axis is their hand deviations in the very next trial. Each dot stands for a single trial. As you can see, the human data is very noisy. But if you take a look at the average data, which is indicated by the black line, you see that kind of a sigmoid shape, that nonlinear learning curve. So on the right-hand side, I show you average data from all the subjects. And indeed, the hand deviation in the very next trial follows a nonlinear learning curve. It's a sigmoid-like, right? Then there are 2 messages you can get from this figure. First, people indeed correct for their errors, and their correction size, their hand deviation, is a function of visual error size. It follows this kind of a stereotypical shape. The second message is the influence of visual error decreases over subsequent trials. So in the next trial, it has a large influence. In the next trial, its influence decreases. That's why the learning becomes smaller. And its influence will continue to decrease in the following trials. All right, this is the data. Now we need to do the model fitting. I just do a quick go through of all those procedures. First, we have our data. We have our actual data, which is your hand deviations in the next trial. We also know the visual perturbations we apply to the subject. So this is the data. But we don't know those model parameters. So we do model fitting by using maximum likelihood estimation. Then we can derive those free parameters. We do this for each individual subject. Once we have those model parameters, we can do model simulations. We just plug in those model parameters, plug in the model inputs, which is the visual perturbation we apply to the subject. We plug all those variables into the model. We can predict where subject hand will go. And lastly, we can compare the model prediction with human data. We see how well they match together. All right. Then I plot the data and the model prediction together. The data is shown as a dashed line. The model prediction or the model simulation is plotted as a solid line. As you can see, they actually match each other pretty well, right? And the model can capture the pattern in the data. All right, then we already know the model parameters for each individual subject. Now we need to interpret those model parameters, see whether they make sense. Remember, I have a model parameter S and a sigma. Using those model parameters, I can estimate the subjective belief of error relevance. What does it mean? Is your subjective feeling whether that error is caused by yourself, estimated by the model. So I plot this estimate. I plot the probability of relevance as a function of a visual error. It has this kind of shape. It actually makes perfect sense. For zero visual error, you are 100% sure that the visual error is caused by yourself. But with increasing visual error size, for example, with 8 centimeter visual error, you don't believe it anymore. You don't believe that visual error is caused by yourself. That's why the p-relevance is decreasing to the lowest point. This is exactly what you expect, right? The larger the error, the less likely is a self-produced error. So this is actually naturally demonstrated by your model parameters. I also plotted the other model parameter, which is the scaling factor S. As I showed you before, the scaling factor S stands for how much people learn from a visual error. And I plot this scaling factor as a function of data t. Data t means data t equal 1 means how much you learn from the previous trial. Data t equal 2, which means how much you learn from the previous trial. So as you can see, the S is getting more positive, close to 0. What this means? If it's a large negative value, this means people learn a lot. If it's close to 0, that means people don't learn much from the visual error. So as we can see, there is a decreasing influence of previous trials. This is exactly what you expected from the data, right? People learn less from the history, but people learn the most from the immediately before trial. So our model parameter captures this trend. All right, we don't stop here. our model actually can make new predictions. We know if people move shorter, they have less motor noise. What this means is in this figure. Remember previously people making 15 centimeter movements. And if I plot their motor error as a function of as a probability distribution, it goes like this, right? Small error is more likely and the larger error is less likely. So the motor error is a distribution. If I ask people to simply move 5 centimeters, they have less motor error. That means this error distribution is narrowed. So they are more likely to have smaller errors. And once I know this knowledge, my model can make further predictions. The further prediction goes like this. The blue line is my old prediction, that for the 15 centimeter movement. And that's the learning curve. For 5 centimeter movement, my prediction is very easy. That because I still apply those visual error from 1 to 80 centimeters. For 5 centimeter movement, I will predict the learning will be much less compared to 15 centimeters. Because those errors become so obvious, it's not caused by the human subject. So they should not adapt to it. Even though they learn less compared to the 15 centimeter, they still will have this kind of a sigmoid learning curve. Okay, let's take a look. So I performed experiment 2 to test this new prediction. The data is shown in black. The blue curve are the experiment 1 data for 15 centimeter movement. As you can see, the data exactly follow my prediction. First, the learning is less, and the learning pattern still follow this kind of a sigmoid shape. So indeed, when people move less, they have less error corrections. The model also make another prediction, that is, I can, again, I estimate those model parameters, so I can estimate the probability of rare elements. The blue line is my old data from experiment 1 for the 15 centimeter movement. For the 5 centimeter movement, the probability of relevance decreased quite a bit. So this is exactly expected. When people move less, they have less uncertainty about the movement error. So they are more certain that the applied visual perturbations is irrelevant. That's why this p-relevance is smaller. I have to remind you, this is not a cross-validation. In fact, I'm making new predictions based on the model. And I did a new experiment, that's experiment 2, to test my model. Okay, the model actually can make more predictions. I fit the model to other people's data from other people's studies. This is one study, it's a human study, see how people adapt to force field. Instead of adapt to visual errors, that's my experiment, people adapt to force fields, and they observe the same sigmoid learning function, and my model can fit that data. This is a data set from monkey experiment, is how monkey adapt the eye movement to visual perturbations. Their data also shows a nonlinear learning curve, is a sigmoid shape, and my model can also predict that. And this is also not cross-validation, it's simply my model making new predictions which fit the data from other people's study. So the take-home message goes like this. So we construct the model, we did the model fitting, we get those model parameters, and by using maximum likelihood estimation. Your job is to interpret those model parameters with respect to data. See whether those model parameters making sense. This is one part of a model use. And the second part is, once you have those model parameters, you can run simulations. You can make model simulations to check how good your model fits are. Ideally, if possible, you can use your model to make new predictions. This new prediction is not even in your own data. Maybe you can confirm the new prediction by running new experiments or using other people's data set to see other people's dataset, whether it can be fitted by your own model. This can be all been done by using model simulation. So I hope this complete research example gives you a sense how to use model fitting for real scientific questions. After all, our goal for doing modeling is trying to linking neural properties, computational mechanisms, and the behavior. In my particular example, I did a behavior study, but I'm interested in computational mechanisms for motor adaptation. That's why I construct a model. If the model fits the data pretty well, which means my model potentially can capture some computational mechanisms. And this will deepen our understanding of neural mechanisms or computational mechanisms of human behavior. Ideally, as I said, you should go beyond your model and make new predictions. This is where you can show the strength of your model. All right, so this concludes my part 2 of the outro. In the third part, I will extend from linear model to generalized linear models. So stay tuned. All right, the third part of my outro, I will talk about optimization and the convex problems. Because today, we only touch upon very simple linear models. But in fact, we can extend to generalized linear models. And why we do that? Because it is related to the convexity. When we talk about maximum likelihood estimation for linear models, we are dealing with quadratic likelihood function. This is what you learned today. This is the likelihood function. Why is quadratic? Because the error function here is quadratic to the parameter theta. And the quadratic function we think is convex because it follows Jensen's inequality. What this means is if I draw a quadratic function like this, and I draw an arbitrary line, arbitrary straight line, and intersect the quadratic function at the 2 points, x1 and x2, the Jensen's inequality basically says the quadratic function between x1 and x2 is below the straight line for any point in between x1 and x2. Say x star is just a weighted average of x1 and x2, and the function value is here, and is definitely below the straight line at its corresponding value. So this is definition of convex. And we will say quadratic function is convex. What this means to us is it has a global minimum. It has a single minimum in the landscape. That will guarantee us to using maximum likelihood estimation to find the best parameter, because we need to find the global minimum, and we don't like local minimums. And why I say convexity can prevent local minima, and it can guarantee us to have a global minimum. Say if I draw parameter theta on the x-axis, on the y-axis I draw the mean squared error, that's the error function. If it's quadratic, if you draw a straight line arbitrarily, you always notice that the quadratic function is underneath the straight line. So you're guaranteed to find the global minimum. But what if you have local minimum? If you have a local minimum, you have a landscape like this, we would say this error function is not concave, because, very simple, if you draw arbitrary line like this, sometimes you will have this function value larger than this line. This just violates Jensen's inequality. So it's not concave, it's not convex. That's why if our function is convex, we are guaranteed to have a global minimum to avoid local minimum. This is very good for our algorithm. It's very good for our maximum likelihood estimation. So we are guaranteed to find the best parameter. Fortunately, we have other functions that are convex. So quadratic function is convex, log function is convex. log 1 over x when x is larger than 1 is also convex. X multiplied by log x when x is larger than 1 is also convex. As you can see, a lot of exponential functions are convex. So can we take advantage of this? Yes, we can take advantage of this property of exponential functions and extend our linear model to so-called generalized linear model. So this is our familiar linear model. It's basically a straight line. And the generalized linear model takes form like this. If you take a look at it, very similar, right? Here you have a so-called linear predictor, that's theta multiplied by x. So theta has a linear relationship with x. And what's new is a link function f. Link function can take different forms, but usually the exponential functions. It could be binomial, Poisson, or gamma functions. So the y, the dependent measure, originally in very simple linear function, y follows a Gaussian distribution. Now, because of link function, y can take other distributions, other exponential distributions. So we extend from linear model to so-called generalized linear model, and y can take all kinds of exponential distributions. This just opens our door to a broad set of more models, right? And I just show you one example for general linear model. And the number of COVID-19 cases actually follows an exponential increase over time during the outbreak. And so it's a linear function. And if we use a link function of log, we can transform it into a very simple linear function. So you take a log, that's your link function now, and you immediately notice it's a new y, this is your intercept, is a constant, this is a slope multiplied by time. So it's a theta 0 plus theta 1 multiplied by x. This is a very similar, very familiar linear function you learned today. So as you can see, those general linear model basically is using a link model can transform all kinds of exponential functions into linear forms. So why we do this? Because there is one nice thing about the general linear model. They're all convex. As I told you before, linear exponential functions tend to be convex. And in fact, all kinds of general linear model, their log likelihood is concave in parameter. This will guarantee us to find a global minimum. That's why I say finding minimum is relatively easy for general linear models. Of course, the details of a general linear model will be covered tomorrow on day 4, so stay tuned. And so this concludes our day 3. I hope you find the model fitting so far so good and so still easy. And in fact, today is a foundation for a lot of new ideas later on. So stay tuned and have fun.